dividing, use least SF. Okay. Question C, while Jackie is cycling at a speed, we better go to a different colour, at a speed of 16.8 metres per second, she collides with a soccer ball that is rolling towards her at the speed of 8 metres per second. This sounds like a momentum or impulse type of question. Soccer ball bounced off in the opposite direction with a speed of 5 metres per second. Okay, the diagram illustrates that too. We've got the ball moving to the left at 8 metres per second, and this is the initial before condition, and 16.8 metres per second to the right. After the collision, the ball's going to the right at 5 metres per second. I guess we're going to be trying to find the velocity of the cyclist. There it is, calculate Jackie's velocity, the magnitude and direction after the collision. You may ignore any effects of friction. So the mass of Jackie and her bike, 72 kilograms. The mass of the soccer ball is 0.430 kilograms. So this sounds like it would be good to use momentum, because momentum we know is conserved. So the momentum initially should equal the momentum finally, the final momentum. So that's the easiest way to do it. This is all in 2 dimensions as well. It's only backwards and forwards, or left and right, depending on how you want to label it. So we shouldn't encounter anything too surprising. So let's do the initial ones to find out what the total initial momentum is. And yeah, we will. Okay, so momentum is mass times velocity. So let's see, 16.8 times by 72.0, 3 SF in all of those. So that's the momentum of Jackie on her bike, plus the momentum of the ball, which is in the opposite direction. So this should be negative velocity of 8.0 times by the mass of the ball is 0.430. So everything is the 3SF except for that velocity. So that's going to limit it in our calculations. And that should equal the final velocity and the initial velocity. In any case, let's just do that calculation really quickly and see what we get. 1206.16 equals the initial velocity equals the final velocity. And that also equals Jackie's velocity. So we'll just call it V, because it's the only velocity we don't know. Velocity times by 72.0. And the ball's now in the positive direction, so it's plus 5.0 times by 0.430. Okay, so let's we know everything except for the V, so I'm just going to solve it for V. In fact, it might be a good idea to write the steps. So V is going to be, or we'll do it this way, 72.0 times V should equal 1206.16 minus 5 times 0.430, which is 2.15. It's a very small velocity. That's because the mass difference is very small. The mass between the soccer ball and Jackie is very small, so there won't be a noticeable change in velocity. And so we're going to then divide both sides by 72.0. Remember, you have to divide everything on the one side. So we've cancelled out that and we're left with V equals whatever we solve that to be. And that gives us an answer of 16.7218, but we're going to round it to, well, we're going to leave it to 3SF because otherwise it'll look exactly the same as the initial velocity. Okay, so, and the direction is to the right. There we go, nice one. D, let's go to a different colour. I found that yellow a little bit hard to deal with. Explain what is meant by an elastic collision and an inelastic collision. Well, for an elastic collision, that means the energy is conserved. So there's no loss of energy. and usually you're talking about kinetic energy. And with inelastic collision, energy is not conserved. So that you've lost energy into the surrounding environment or out of the system, and whether that's through friction or heat. I guess friction and heat are sort of similar things. Heat, it could be light in an explosion, but it all depends on the situation. In the above situation, momentum is conserved, even though you might not need to have conserved the energy. And this is, I think, what the next question gets at, so we'll cruise down to there. Describe what you would need to do in order to determine whether this collision between the bike and soccer ball is elastic and inelastic. There we go, I talked about it before. You need to find the kinetic energy before and after. And you need these velocities that you've calculated for momentum. If EK goes down, then inelastic. Simple as that. E. Explain how the force exerted by the ball on Jackie and her bike is dependent on the duration of the time on impact. So this is an explain, but the formula, and explain how the force exerted by the ball on the Jackie and her bike is related to the force exerted by Jackie and her bike on the ball. So there's two forces going in both directions. First part of this, I'll circle that because we've got two parts. Remember, there's two parts. First part, we'll call that one there. Explain how the force exerted by the ball is dependent on the duration. Change in momentum is equal to force times the change in time. Okay, because it's talking about the duration of time on the impact. As the duration on time increases, the force must decrease for the same change in momentum. And vice versa, if you decrease the time, you'll increase the force. Okay, this is the impulse, concept of impulse. Second part, I'm getting long here, so let's be quick. Explain how the force exerted by the ball on Jackie and her bike is related to the force exerted by Jackie and her bike on the ball. So, making that clearer, you've got the force that Jackie on her bike, this is my rough bike, is exerting that way, and then you've got the force by the ball exerted that way. And this is, I can never remember which of Newton's laws, but for every action there's an equal and opposite reaction is how you might commonly hear it. And there has to be two forces kind of going on here. There's the force applied this way by Jackie and her bike onto the ball. As the ball compresses, there's the force applied in return. That force must be lower than the force applied by Jackie in order to get the ball to accelerate in the opposite direction. Okay, so yeah, I guess the important thing is that the forces are the same size, but what we have to deal with is the change in momentum to explain why the ball moves in this direction after the collision rather than Jackie moving in this direction. She's of a much greater mass, much greater momentum overall, so she absorbs the momentum through the force that's applied, equal and opposite force, and the ball absorbs some of her momentum. And because she's so large, it's very negligible for her, and the ball's so small compared to her that it's more obvious, so the ball travels in this direction. That's what it's getting at. Okay, can be a little bit confusing. Long video, there we go, thanks.